Hello everyone. Let us continue the third part of today's class. Okay, let us go back to the blackboard. Okay, we are solving problem 2 of handout and on page 71, chapter 2. Okay, so from equation 95, we know that f of x is equal to x modulo 1. Okay. So according to the definition of the modulo operation, okay, x modulo 1, okay, is the remainder R of x divided by 1. Okay. In nearly all computing systems, the quotient Q and R satisfy the following conditions. Okay, let us see. Okay, x is equal to 1 times Q plus R. Okay, this is equation 2. Okay, and next, the absolute value. Okay, of R is smaller than 1. Okay, this is equation 3. Okay. So many implementations used truncated division. Okay, truncated division. Where the quotient is defined by truncation integer part. Okay, so Q is equal to trunk of x over 1. Okay, this is equation 4. And the name of the function should be non-italic. Okay. Excuse me. And okay. Thus, according to equations 2 and 3, okay, this equation and this equation, the remainder, remainder would have the same sign as the dividend x. Okay. So same sign as the dividend. Okay. The quotient is rounded towards 0. equal to the first integer in the direction of 0 from the exact rational quotient. Therefore, okay, excuse me, f of x is equal to x modulo 1. Okay. Okay, and is equal to r, and is equal to x minus 1 times trunk of x over 1. Okay, so this is equation 5. Okay, let me align at the okay, so okay, let me align at the equality sign. I can't align. Okay, what's the problem? I don't know. Okay, so it is non-italic. Okay. Okay, so let me align at the equality sign. Okay, good. And the trunk should be non-italic. Okay, and then I add the equation number. Okay, good. Okay, for example, f of 1.23 is equal to, okay, now x is equal to 1.23, so it's equal to 1.23 minus trunk of 1.23 over 1. Okay, trunk should be non-italic. Okay, so it is equal to 1.23. Okay, 1.23 over 1 is equal to 1.23, and truncated it. Okay, that is only take the integer part. So the integer part of 1.23 is equal to 1. Okay, so this is equal to minus 1. Okay, and this is equal to 0.23. Okay. Okay, so let us align at the equality sign. Excuse me. Okay. So another example. Okay, let us see if x is a negative number. Okay, f of negative 1.23. Okay, is equal to negative 1.23 minus trunk negative 1.23 over 1. Okay, so trunk should be non-italic. Okay, and the negative sign should in the numerator. Okay, like this. Okay, so it is equal to negative 1.23 minus, okay, negative 1.23 over 1 is still equal to negative 1.23. And after taking the truncation, Okay, so that is take the integer part. Okay, so and please note that the potential is rounded towards 0. Okay, so trunk of negative 1.23 should be negative 1. Okay, so it is equal to negative 0.23. Okay. Excuse me. Okay, so this is equation 7. Okay, so now we can draw the graph of f of x. Okay, let us see the graph. Okay. Okay, so let's draw the graph. Okay, so this is okay, like this. Okay, and it is x, and this is f of x. Okay, and this is 0, and this is 1. Okay, and 2, and 3. Okay, and this is 1, and this is negative 1. Okay, and this is negative 1. Okay, negative 2, and negative 3. Okay, like this. Okay, so the graph should be like this. Okay. And this. And this. Okay. Okay, and on the point negative 1, okay, should be like this. Okay, and okay, this. Okay, good. Okay, so okay. Okay, let me. Okay, good. Okay, it is already a group, so I need to make this 上及下. Okay, like this. What's the matter? Okay, so so let me choose this figure. Okay. Okay, good. Good. Okay, so I should select all the thing. Okay, and combine this into a group. Okay, and okay, 上及下. Okay. Okay, so I can paste it here. Okay, and no, not 上及下. Okay, 语文字排列. Okay, like this. Okay, so obviously excuse me, f prime of x is equal to 1. Okay, because you can see that the graph of f of x, the slope of the graph of f of x is always equal to 1. 1, 1, 1, 1, 1. Okay, so this is equation 8. Okay. Okay, that's all. Okay, black square. Okay, so let us go back to the handout. Okay. Okay, so this is equation 96. Okay. Okay, next let us see multi-layer perceptron. Okay, first let us see this figure. Okay, figure 51. It is a two-layer neural network capable of calculating XOR, that is exclusive OR. The numbers within the neurons represent each neuron's explicit threshold. Okay, so in these 3 red perceptrons, okay, the threshold of this perceptron is equal to 1, and the threshold of this perceptron is equal to 2, and the threshold of this perceptron is equal to 1. Excuse me. Okay, which can be factored out so that all neurons have the same threshold, usually 1. Okay. So next, the numbers that annotate. Okay, I will introduce the meaning of annotate later if we have enough time. Okay. Arrows represent the weight of the inputs. Okay, so from x to this perceptron, the weight is 1. Okay, and from x to this perceptron, the weight is 1. And from input y to this perceptron, the weight is equal to 1. And from the input y to this perceptron, the weight is equal to 1. Okay. And from this perceptron to the output z, the weight is equal to 1. And from this perceptron to output z, the weight is equal to -2. And from this perceptron to output z, the weight is equal to 1. And finally, the output z is equal to XOR of x and y. Now, of course, this weight is also equal to 1. Okay, this net assumes that if the threshold is not reached, 0, okay, not -1, is output. Okay, note that the bottom layer of inputs is not always considered a real neural network layer. Okay, like this, like x and y. Okay, sometimes it is called the input layer. Okay. Okay, so next, okay, please see figure 51. Okay, we have already seen figure 51. Okay, this class of networks, okay, which denotes the multi-layer perceptron, consists of multi-layers of computational units, usually interconnected in a feed-forward way. Okay, each neuron in one layer has directed connections to the neurons of the subsequent layer. Please see figure 50b. Okay, let us see figure 50b. Okay, so here. Okay, good. This is figure 50. Okay, this is B. Okay, we can see that there are 1, 2, 3, 4, 5 input neurons, and 1, 2, 3 hidden neurons, and 1, 2 output neurons. Okay, and there are many edges between them. Again, they are fully connected. Okay, so each edge has its weight. Okay, so figure 50b is the extension to a multi-layer perceptron including more than one layer of trainable weights. Okay, in this example, the network includes 3 layers: input, hidden, and output layer. Okay, so here is the input layer, here is the hidden layer, and here is the output layer. Okay, each connection between 2 neurons is given by a certain weight. Okay, for example, the connection, this connection between this neuron and this neuron is given by a certain weight. Okay, and so on. Each connection has its own weight. Okay, so let us go back to figure 50b. Okay. In many applications, the units of these networks apply a sigmoid function. Okay, what is a sigmoid function? Okay, we have explained it before. If you forget, you can click on this hyperlink. Okay, and the handout will jump to the solution to problem 1. What is sigmoid? On page 62. Okay, let us go back to the sigmoid function. Okay, as an activation function. Okay, however, sigmoidal activation functions have very small derivative values outside a small range. Okay, what does this mean? Okay, let me show you. Okay, let us go to the sigmoid function. Sigmoid. Okay, sigmoid function. And let us see figure 34. Okay. Okay, figure 34 is a kind of the sigmoid function called logistic curve. Okay, so we can see that here the slope is equal to 0, and here the slope is equal to 0. And in this region, the derivative is very small, and so is in this region. Okay, so only in this small range, okay, the sigmoid function has a large derivative. Okay, so let us go back to the sigmoidal. Okay, so however, sigmoidal activation functions have very small derivative values outside a small range and do not work well in deep neural networks due to the vanishing gradient problem. Okay, I will introduce what is a vanishing gradient problem later if we have enough time. Okay, alternatives to sigmoid activation functions that alleviate. Okay, it is 25 minutes. Okay, so we have finished teaching the class in this semester, and I wish you all the best in the final exam and in the summer vacation. Goodbye.